Right. Thanks for the introduction. Yeah, and the invite to talk. Glad you guys were able to slide things through my travel schedule and stuff. Okay, so I am pretty rusty at doing talks. It's been 3 years since I've given a talk. I've been at Amazon for about 2.5 years, working at Amazon. Can you hear me or? Hi. You good? I'll try to.
Can you have us wondering, we'll have a microphone.
I guess not.
We don't have one in the room because it's a room microphone.
I'll try to project as much as possible.
I could be.
Okay. Yeah, so I've been working at Amazon with Amazon Robotics, and that's inspired some of the thinking that I currently have about the directions my research is moving in. And I'd like to kind of articulate some of the challenges that I'm currently thinking about in this talk, and then I'll focus a little bit on some of the research we have going on. Before getting into that, I'll just give a little bit of an introduction to the general area that my group focuses on. So we try to draw on tools from game theory and economics to capture strategic behavior and competition. So we'll see in some of the examples that now we're not just thinking about robotics and control problems where you have humans in the loop, but also AI agents that we need to be able to reason with and about. So these tools become important for that purpose. And then in addition, we draw on tools from control theory and statistics to reason about dynamics and uncertainties. So as we'll see also in the talk, a lot of times these AI agents or algorithms are adapting in time, and so they're not stationary, and we need to be able to kind of deal with dynamics. And then finally, and this is really motivated by some of the work at Amazon, we want to think about the actual practical implementation of the algorithms and theory that we develop. So one of the things that I've become aware of is really the importance of thinking about quality versus quantity of data that you get, and then also sort of the machine learning operations and how that impacts the different algorithms that you design and what you ultimately implement. So yeah, my group kind of pulls from these different areas. It seems pretty diverse, but all of these tools are somehow necessary. Okay, so let me motivate the two pieces of work that I'll talk about with a little bit high level kind of examples. So there's this push in general to try to use very large models. And this introduces new modes, new fragility modes, especially when we talk about robotics or control systems. So traditionally, we think about training a machine learning model where we have very task-specific data. We maybe learn some supervised or unsupervised machine learning model, and then we go and deploy that particular algorithm in some context. Maybe we monitor and then we retrain. So maybe there's a feedback loop here, but it's not necessarily a true feedback loop in the way that we think about it in control systems. And so progressively, we're kind of moving towards this new model paradigm where we take multiple modes of data. So you can think about in the context of autonomous vehicles where you maybe have LiDAR, you have map data, you have time series data, you have RGB images, all kinds of sources of data. You pull this together and then you train a preliminary model, a very large foundation model, if you will, that's meant to extract some kind of representation of the world from these various data sources. And then we fine tune that model for a particular task. So maybe you want to do segmentation for the purpose of building a perception action loop. Maybe you want to design path planning policies for parking an autonomous vehicle, something of this nature. So all of these different tasks potentially build on the same type of model or exact same model. So there's issues related to propagating this sort of shared model architecture, shared training set that can cause problems when we think about the safety and security of these algorithms. Similarly, we're now fine-tuning them. There's this kind of feedback loop. You can have a feedback loop that goes all the way back to the training data, or just to the sort of fine-tuning phase. And in this feedback loop, we rely on humans that are very expensive to sample to be experts and label data. And increasingly, we're also relying on other AI large models to provide input. So we now have this kind of closed loop process in the way that we train models. And so then this means that if you have any spurious correlations or biases or potentially adversarial inputs upstream, this gets propagated and then amplified through this feedback loop, and then the fact that we're sharing the model architecture across a bunch of different tasks. So one example where we've seen some sort of unexpected outcomes, or potentially expected if you actually thought about it before deploying it, is a setting that I've been thinking about where we're looking at, say, a warehouse. You can be Amazon, you can be Walmart, or any large company that's distributing goods through like an online platform, and you want to store a bunch of goods in a very large warehouse in some kind of storage pod so that when people order it, you can pack boxes and then ship it to them. In the case of Amazon, there's hundreds of these very large warehouses. On each floor of the warehouse, you have thousands of mobile robots that are moving these storage pods around. And in particular, moving them from a center location out to either human associates or other robots who do the picking and packing. So there's kind of a really hard congestion management or prediction task here. You want these robots to be safe, especially if humans have to intervene on the floor. You also want to assign tasks to them efficiently. So we try to use all the data we collect from these thousands of robots to build out foundation models that can then be fine-tuned for very specific tasks for each of these type of robots. But what can happen, especially if you have these shared model architectures and you're not thinking about other agents, you can have these kind of silly behaviors. So actually, I found this on Reddit a few days ago. Maybe you guys saw it as well. And these kind of robots just kind of get stuck in this infinite loop. And this might seem, okay, well, that's a silly example, but we also have this with autonomous vehicles. I don't know if this is Cruise or Waymo, it's one of the two. But these cars kind of get stuck in Waymo, okay, yeah. They get stuck, they can't get out of the parking lot. And then this is a more serious situation. This is in San Francisco, it's a little hard to see with the light, but basically you have these autonomous vehicles also getting stuck, and it's in the way of like where pedestrians are walking and things like that. So there's potentially dangerous outcomes that can happen. Okay, so that's one set of issues related to poor uncertainty adaptation, bad generalization, not thinking about other agents when we deploy these algorithms. But there's a whole other set of interesting and hard problems related to kind of thinking about this maybe more from a multi-agent or game theoretic perspective. Again, maybe with our control theory hat where we care about dynamics. For example, coming from the fact that we use these fine-tuning loops where the agents are learning and adapting. So you can take, just your own personal use, for example, with some chatbot, maybe ChatGPT. What it's doing is not exactly being stationary when you query, right? It might be appending your queries to its set of tokens or its set of prompts, and then reweighting a distribution to kind of tailor its responses to you. So this is adapting over time. And increasingly, we're going to get to a situation where they're actually sort of online fine-tuning with, say, gradient-based methods that are fast. So you have these dynamics that are happening. And then in addition, we're eventually going to get to a situation where we have network interactions between these AI agents. So one example might be using an AI proxy for a human who's trying to plan a travel itinerary. And this proxy goes and queries a network of other AI entities, for example, a representative of, say, a ride-sharing platform, an airplane company, and so on. And so these things will interact. And so all of the problems that we think about for humans in the loop become exacerbated and kind of different because we don't necessarily know how to reason with or about these AI agents. Okay, so I'm thinking about problems in these kind of spaces where we have these challenges. And in today's talk, I'm just going to focus on two problems. So not necessarily on the training of these models, but more on potential cases where they might be used in different applications. So the first part, which I'm going to apologize for, is going to be more theoretical, is going to focus on principal agent problems where the agents are dynamic and moving in time. So the non-stationary aspects I mentioned. And then the second part will be a little more applied, focus on how to design uncertainty adaptation methods and safety critical settings. Okay, so to the first part, this is joint work with my student and then colleagues at the University of Washington. Yes, it focuses on principal agent problems, stochastic principal agent problems. So the general setup is as follows. We have a principal. So I think in the robotics, human robot interaction, sometimes this might be called the ego agent. Sometimes it's called the decision maker. In game theory, we call this the principal. So I might mix up different names here, but principal, decision maker, that's basically this sort of primary agent that will think about from their perspective how to design an algorithm. And so in this context, they want to solve this stochastic optimization problem, or they want to optimize with respect to their choice variable u, but the distribution that the sort of stochasticity here depends on their action through the fact that the action influences the preferences or the game amongst a set of agents. So you can think about these maybe as those the Kiva style mobile robots in a warehouse, or some set of, say, skilled AI agents that you're querying and interacting with. So for each U of the principal that induces a game amongst these agents, these preferences are unknown to the principal, and there's additional environment stochasticity that might also depend on their action. And so we're going to deal with two challenges here. So first of all, the agents are going to be learning. So there's non-stationarity. And then this issue I mentioned where their preferences are unknown. And our goal is going to be to design an algorithm that sort of stabilizes these agents so that we can then optimize through their behavior and find a game theoretically meaningful equilibrium from the perspective of this principle. Okay, so in an ideal world, the agents would be behaving in equilibrium. So this X star here is the induced equilibrium of the game amongst the agents. So ideally, they would be playing sort of a best response as indicated here, and the decision maker could optimize with respect to that, and the environment would be otherwise stochastic but stationary. But that's not what's happening here. We have these agents using some subset of algorithms that are changing in time, given their past actions and the actions of the principal. So everything here on the right-hand side is moving with time, and the principal still wants to sort of stabilize and find an optimal solution to this problem. So to make our lives somewhat easy, we're going to make some assumptions on the behavior of the agents. We're going to assume that they're heterogeneous, no-regret learners, where the class of algorithms satisfies this row contracting property. So in each time step, they're contracting towards some equilibrium, up to some stochastic noise. So you can say, okay, maybe that's restrictive, but there's actually a broad class of update rules that satisfy this. Lots of traditional ones in learning and games, and then also multi-agent RL variants. So essentially anything that can be modeled as a stochastic approximation update with a contracting property kind of falls in this category. The second assumption we're going to make is that the game, for every action of the principal, the induced game is strongly monotone. And this is for the purpose of having the existence of an equilibrium for every U. If we didn't have that, then this whole problem would be ill-posed, right? You might have multiple solutions for the constraint here. There's plenty of results in hierarchical decision problems, Philo optimization. You try to deal with that or other non-smoothness. So I'm going to kind of set that aside to primarily deal with the non-stationarity, and then we can revisit that in future work. So this gives us existence of an equilibrium that the agents are for each U are potentially tracking. Okay, so we're going to first deal with the challenge one, which is the non-stationarity. So the agents are learning. So for the purpose of discussing how we're going to deal with that, let's just assume that the principal is updating according to some gradient descent procedure. We'll talk about what gradient they're following and what that means about the equilibrium that they're tracking. But just assume for now they're doing this update with some step size eta. Then our goal will be to show that in finite time, we can bound this sort of tracking error on the left-hand side here. Without going into the details, using tools from optimization, you can break this up into three terms. Normally, if you don't have any dynamics, this drift doesn't exist. You just have a performance error that depends on the initial condition in a noise term that deals with the stochasticity. But in our problem, the agents are moving, so we have this drift term, which captures the difference between the agent's actual behavior and the induced equilibrium at each time step. So we want to be able to control this and make this small, in particular, make it small relative to the noise, so that we can then use our standard sort of tools to bound this tracking error. And so what we're going to do here, so we don't have all the usual assumptions. The Sackelberg game isn't jointly monotone. We don't have any explicit coordination on choices of step sizes. Agents are updating independently, but we still have some elements of control from the principal's point of view. We can choose the step size, which is pretty key in optimization. And then we can also modulate the action. So in our case, what we're going to do is employ a type of timescale separation where we induce, we hold our action fixed, similar to a zero order hole control, for a certain amount of time to stabilize the dynamics. Seems pretty natural, but I'll show after this slide that it's necessary to do that. So just to kind of give the picture, what happens is the decision maker or principal deploys an action UT that induces this gain or equilibrium amongst the agents. The agents flow forward from wherever they were at time t-1 to a new point at. And we can see we have the sequence of gaps that are the drifts that are going to show up as extra error terms in the decision maker's problem. So the idea is if we can sort of design how long we flow forward for, then we can carefully bound these gaps to get sort of an optimal finite time tracking error. Okay, so as I said, you might say, okay, well, why do we need to have this timescale separation? Can't they jointly learn? And it turns out that there is a non-measure zero subset of games for which the finite or the timescale separation is strictly greater than 1. And so just as an example, this is a quadratic game. And so it turns out that you have kind of hybrid-like dynamics that look like a linear system here. So you have this first term, this is going to be the dynamics that are running for tau time steps. So you have one set of dynamics there, and then it gets hit with the sort of joint update by both players. So we can try to find what the tau should be so that you end up getting this joint system is stable, so the eigenvalues are less than 1. And it's really non-trivial to kind of see what the structure or like how tau depends on the game parameters. So this is one particular trajectory I'm showing, but like it can be any kind of nonlinear behavior, and importantly, tau in general is not equal to 0. If anybody wants to solve this problem, like construct a theoretical bound, I know how to do it. I just haven't had time to sit down, write it down. It's a really cool old tool from control theory dating back into like the 60s, probably guard map. I don't know, there's a previous paper with one of my students who spent like a year thinking about this, quite interesting, definitely from a linear algebra point of view. So if anybody wants to work on this, just send me an email and I can set you up. Okay, so coming back to the problem, we have our decision maker deploying action U. We flow forward for tau time steps. We get to a new point for the agent, and we want to bound that drift. So using the fact that it's row contracting, you get the right-hand side of this expression here. And the important bit to see is that the time varying piece, so the last term is the noise, the first term is the time varying piece. It depends on where the gap between where the point they're tracking and where they started. So it's basically the initial condition for the tau time update. And we want to bound this whole right-hand side with a term that's proportional to the noise of the decision maker times their step size. That way they can then choose their step size accordingly to control that error. So in order to do that, we need a uniform bound on the initial condition, and that is time varying. So we have to figure out how to bound that gap. And the way that we end up doing it is get some intuition again from this plot. if you just look at this, break it up using triangle inequality, you have the gap between the two equilibrium, and then you end up with another term that is just the previous drift term from time step t minus 1. So now we have this kind of iterative process where if we can control this gap with the step size, because it just depends on the gap between ut and ut minus 1, then we can iterate on this whole thing and get a sequence of bounds on these drift terms. So that's sort of the intuition. We can actually construct these bounds theoretically, and more importantly, we can do them in an optimal way. So how that works is as follows. So we now just take the tracking error for the agent. So this is this new notation for the equilibrium induced by UK. So we can bound this tracking error by breaking it up again into a performance error. It depends on the initial condition, which this is not time varying anymore. It's where the agent started originally. A noise term, and then another drift term that comes from the gap in the induced equilibrium. And so we want to optimize the right-hand side and find basically a finite time target accuracy and a time, how long we need to run the algorithm in each epoch in order to get as tight a bound here as possible. So interestingly, we can kind of carve up the space of what's possible for that right-hand side in terms of the two terms. So this noise term and then the drift term. It kind of separates out different regimes. So to see that, we'll look at stochastic gradient play. It's a little easier to unpack the optimal target accuracy in that case. So I just basically replaced the general row contracting update now with the parameters for stochastic gradient play. Agents are following their individual gradients here, and gamma is the step size. And if you recall, mu is the strong monotonicity parameter for the induced game. So what happens as t goes to infinity, this term essentially is negligible. And then we're just left with these two terms that are otherwise constant. So we want to determine the optimal possible error with respect to this term. So we can optimize that given gamma. And this gives us sort of two regimes relative to this drift to noise ratio. Sorry, that's the wrong button. Okay. Okay. So don't worry, the theory part's almost done. Yeah, so we can break this up. So there's what's called the high drift to noise regime. So this is basically, you remember delta A is induced by the principal's action. So this is where they're just moving to, like they're holding tau fixed for too long. So there's too much drift in the equilibrium relative to the noise of the agents. So in this case, basically all the agents can do here is just pretend the problem is deterministic and employ the largest step size possible for a deterministic problem. And you get kind of a standard tracking error as shown above. And there's nothing more you can do to really improve that tracking error. On the other hand, in this low drift to noise regime, so the principal has effectively controlled the drift using its step size so that it's small relative to the noise. In this regime, we have something interesting. First of all, we can choose, if the agents choose the step size proportional to this drift to noise ratio, and it's in their best interest to do that to get the best iteration complexity, then we get this, the following sort of finite time bound that's dependent on the noise. Because it's dependent on that noise parameter, you can employ tools from stochastic optimization to actually deploy, like run this in stages to hit a target accuracy that where the iteration complexity is essentially what it would be if you were just running standard stochastic gradient method in a single player setting. More importantly, we can state this theorem in as a high probability bound, which is very important for these game settings, because when the decision maker deploys or principal deploys an action, it is unlikely, because the agents are changing in time, it is unlikely that they can deploy a different action with the very same initial conditions and get the same, or get like a new trajectory with exactly the same algorithmic behavior, because the agents have sort of changed. So we want to say if I deploy as the principal an action once, then I can get, with high probability, a guarantee on what the tracking error will be as a result of that. So we can do that here. Okay, so now we've kind of determined that it's possible to bound the sequence of initial conditions using this drift and noise decomposition, and we've also determined what the optimal target accuracy can be, as long as the decision maker can control that drift using its step size. So essentially what we've done is said, okay, we have the ability, we can get this R that bounds sort of uniformly this initial condition. We can set tau accordingly, so how long we deploy the action, and do it in a way such that the epsilon tau, so the target accuracy for the agents bounding the drift term, is proportional to the step size times the noise. So now what the decision maker can do is just optimize their step size in order to get convergence. But the question is, to convergence to what? So this brings in the second challenge, where I told you to kind of ignore what the update or the gradient update the decision maker is doing. So let's talk about that now. So again, coming back to the ideal scenario, you would have a best response map. It will be known to you, and you could as a principal, you could optimize through that best response map. But in practice, what that means is that you need a way to stochastically sample this full gradient, where you not only differentiate through the explicit dependence in L on U, but also through the dependence of your distribution, and therefore the agent's response as it depends on you. This is not stochastically queryable, and we don't have any map or any understanding of what the agents are doing a priori. So that makes computing this term all but impossible, with the exception of some methods I'll talk about, which are sample inefficient. Okay, so just coming back to the update. So the agent's question is, what is this G going to be? So we've shown that we have this kind of tracking error where we have a noise term, and then we've set delta here to be proportional to that noise term. Okay, so then we're going to consider two cases. A naive principle that only uses the first term in the gradient. So this is common in machine learning to do repeated gradient descent. Essentially ignore distribution shift. You just do an update based on that stochastically queryable part of your gradient, and then maybe you detect drift and you update. So that's a very practically motivated kind of principle. And then the second one will do what we call a strategic principle that will try to optimize through that decision dependence, the unknown model, but do it with a zeroth order method that is has very high sample complexity. Okay, so what that means is that the equilibrium that the naive agent is tracking is what's called a performatively stable equilibrium. So this is essentially a Nash equilibrium of the gain between the principal and all the agents. You can see that from this. If you forget about the environment being decision dependent, this is what makes it not exactly a Nash. Then all this is saying is that the decision maker is playing a best response to the agent's best response. So that's exactly a Nash equilibrium. So that's when the decision maker only uses this first part of the gradient. When it is able to estimate this full gradient, then we can show that what it's tracking is the Stackelberg equilibrium from before. Okay, so just kind of very informally, the results look like the following. Our naive decision maker runs repeated gradient method, finds a suboptimal equilibrium. So optimal would be the best thing you could do, which is the Stackelberg. So it finds a suboptimal equilibrium, but does it in a way that is way more sample efficient. You can see this compared to what is the strategic agent's sample complexity, where they use a zeroth order method. They find the optimal Stackelberg equilibrium, but of course they have a very, very bad sample complexity. So this opens up the question of, well, when is it really worth it to do this high sample complexity method? Do I really care that the agents are reacting? And so this term, this L here captures the how reactive the agents are. Basically, bound like this, Lipschitz bound on the best response of the agents. So this is capturing how reactive the agents are in equilibrium. And we can bound the gap between the performably stable and the Stauffenberg equilibrium. Happens to be proportional to some Lipschitz constants of the decision maker's loss. That's what the other L's are, without going into the details. And then this agent reactivity. What this plot is showing is an example where if you want the same quality equilibrium, meaning the UPS is like within an epsilon distance of U star, which is the guarantee you would have for your derivative-free method in the strategic case, then depending on how reactive the agents are, it can be better to just run that derivative, the repeated gradient method, up to a point where when the agents are very reactive. At that point, the sample complexity explodes because your guarantee that you need to stay in that epsilon ball is getting smaller and smaller, so proportionally you have to run it longer. Whereas the derivative-free method, its sample complexity doesn't grow as quickly in this regime as a function of the reactivity. So this exposes like a lot of interesting questions about when we should actually think about how reactive the agents are versus like what update we're using, which gradients we're using. And so we have some recent work, which I won't go into, on thinking about estimating this reactivity and then optimizing with respect to our estimate of this plus some uncertainty that can help us think about trading off between sample complexity and performance. Okay, coming back to the high level. So this was a little bit of a deep dive into some theoretical results, but really the algorithm design principles translate across domains. We've been applying these ideas to a number of problems. So the high level ideas, you have a principle, they're facing a non-stationary dynamical system that it comes from other agents learning, and they need some way to control that behavior to be able to optimize. And so in the first part of the talk, we did this through carefully designing how long we deploy the same fixed action that's used to stabilize the dynamical system, that is the agents. We've done that also in principal agent bandit games. So these show up in practice for things like, giving out incentives in online platforms to get people to participate, either buy something, come to your restaurant, etc. So this shows up also in military scenarios where you have two teams competing and you want to influence the behavior of the other, you're being strategic and want to influence the behavior of the other team. And so in these contexts, we also use a stabilization type result where the agent here is this red X. It's learning over time because it doesn't know its own reward. And so we have to play bad arms infinite, forever, basically. We always have to explore bad arms in order to stabilize this agent. So we have some results on this in a couple different settings. We also have results on thinking about the same kind of control sort of perspective for a number of other machine learning tasks. So interactive conformal reasoning in embodied AI, where you leverage a large language model in a query response kind of fashion in order to decide where to explore next to learn about your environment. And here, similar to this prediction powered inference, where you're trying to select amongst a bunch of other models whose performance you don't know, and you're learning over time. And then also in multiplayer performative prediction, where here we use the leverage of idea of continually exciting the system through injecting noise, but the purpose is the same. You want to excite the system so that you can learn and then optimize through what you learn. So the principles apply more broadly. Okay, last part will be much shorter and more applied. So I'm going to talk about the second kind of issue that I brought up at the beginning, which is poor uncertainty adaptation in a lot of our implementations, and what are some ways in which we can develop methods to better adapt to uncertainty. And I think several of you kind of work on or have worked on similar problems. So hopefully this is a little more familiar. And this is joint work with my colleague Karen Young and Arrow and our students, Jake and Kazuki. So this problem, we're going to think about safe planning in multi-agent situations. So you can think about like the car example I gave at the beginning, where you have an autonomous vehicle and it's trying to navigate some street where humans are acting as like pedestrians, for example, and you want to be safe, but you also want to reach your sort of target goal. And so a lot of papers exist for safe planning with conformal type methods, but most focus on adapting to the uncertainty around the specific agent state or the agent's model. Here, we're going to adapt the uncertainty directly to a safety certificate, which comes from a control barrier function. So let me give a quick primer on this in case folks aren't familiar. So essentially, you have a control-defined system, and you have some safe region in your state space, and you want to ensure that if you stay in that safe space, you stay in. If you start in that safe space, you stay in it. So what this condition here, without going into the details, is saying is that if I start in the system or in the safe space, then I don't move too fast towards the boundary, that there doesn't exist a control that can push me back in. So there's always going to exist a control that can force me to stay in the safe space. It's basically what this is kind of guaranteeing by encoding the safety buffer here. It also says if I start on the boundary, then I'm not going to escape. That's all this is doing. It's showing that we're ensuring that we have existing controls that make sure that our safety set is forward invariant with respect to the control dynamics. Once you have the safety set, the question is then how do you synthesize a control law? There's many methods. This is a great review paper by Aaron and friends. It has a lot of techniques. One we use is setting up your problem like a quadratic program. So you take a nominal control law, doesn't have to be safe a priori, you just have some baseline control, and you optimize with respect to that, encoding your safety constraint here, right? So this is our safety candidate function H for guarding our safety set, the lead derivative along the dynamics and that safety barrier. So we want this to be positive. When your H class has certain structural properties, then you can encode this as a quadratic program. Again, lots of tools to be able to do that that you can read about in this video. All right, so to our setup, we again have a principle. Think about this as some robot, autonomous vehicle, whatever you like, and a bunch of agents. Think about these as humans that you don't want to run over or run into. So we have our continuous time control-defined system, inputs from our agents and principle. And to apply these conformal methods, we really need to map this into a discrete time domain. This is where most of the tools exist for conformal methods. So we either take this to be a event-triggered discrete time system, where like you're sampling from that system, and that triggers data, so we can model that in discrete time, or you do direct discretization and you do zero order hold. I'm not going to go into the details of that, or how you would kind of transition the continuous time control set to a discrete time one. You can just know that there are, again, lots of methods to do this. We borrowed some results from Sarah, Dean, and others from this paper cited here. Essentially, what you do is you just bake in like a little safety parameter. I apologize, this is the same notation with step size from before. This eta bakes in errors due to your discretization or your sampling, etc. So what we would like to do, ideally, is solve this optimization, this planning problem here, subject to some safety constraint that encodes the safety guarantee we talked about before. But the problem is that this guy is unknown. So we don't have a way to compute this term, because we don't know what the agent's doing. We don't exactly know what humans are going to do in our environment from the robot's point. So a natural thing to do is say, okay, well, maybe I can encode this as a high probability constraint if I have a policy for the agent behavior. If you did, you could write this in a high probability way with respect to that uncertainty. And then you'd ideally have safety limit like this. That says, as long as I start safe with high probability, then I'm going to remain safe, not just at the next discrete time step, but on the entire interval in continuous time between those two steps. We don't have this, obviously. We don't have even samples. We don't have the exact policy. So we try to estimate this from data. So in our numerical examples, we use data from, we look at pedestrian data from this ETH pedestrian data set that has like, kind of apparently a good approximation of what humans do in different environments. So that's one example. So you get an estimate of a policy, but that estimate can be wrong. So our hope is to encode the error in our estimate in such a way that, and be able to adapt to uncertainty as we're getting new data online so that we preserve this guarantee. Okay, so I won't go into the details here, but basically we have our true control barrier certificate here on the top. UA there is unknown. We have an estimated policy for the agent, so we can compute an estimate for the safety guarantee. And then our desire is that we can encode a constraint that guarantees that B hat is not too far from B. So we get this idea by making in what we call safety margin here. If we design this correctly and then adapt it over time correctly, then we can still get this guarantee that you start safe, you remain safe. And then with our estimated set here, we can find a safe control law using this quadratic program proof. So the idea with the safety margin is that the more uncertainty you have, so the bigger the gap between the estimated and true safety barrier function, the larger lambda should be, which will be more conservative and it will constrain your robot's decision space accordingly. And then you have the opposite effect, less uncertainty, smaller lambda, so you're going to be less conservative. You have more freedom to choose your, your control action as a result. Okay, so won't go into details here, but one of the kind of challenges is that the data, so normal conformal methods require some kind of exchangeability or IAD type data. We don't have that, it's a dynamical system. And so we want to be able to adapt to uncertainty. So what I'm showing here is just non-exchangeable, what the adaptation would look like as you get new data for non-exchangeable conformal prediction. Essentially, it's take a worst case bound, ensure that your lambda satisfies whatever risk level you're willing to tolerate with respect to that worst case bound, and then you get a next step guarantee. So in practice, we do some combination of this with an online learning method to adapt lambda. So we'll go into the details there for the sake of time. But essentially what we end up getting is a guarantee that our estimate at the next time step is close to the true thing in terms of safety, up to our safety margin, and then some term it captures the non-exchangeability of the data, which is what beta is, and then alpha here is our specified risk tolerance. So we get a high probability bound if this holds. Okay, so then given that, if we choose our controller at the next time step, we have a high probability guarantee that will stay safe. And this is kind of the general algorithm. You learn your model offline, you observe new data, you append that data, you adapt lambda accordingly. You could also update your estimator. I'm leaving that aside because that requires much more massaging of your data set. And then once you have your adapted lambda, your safety margin, you can construct your safe set estimator and then optimize and rinse and repeat. So just quickly to show an example of how this works relative to other baselines. As I said, we learn a model for humans using this ETH pedestrian data set, and we just create a simple simulation. We're extending this to some real experiments with mobile robots, jointly with Bechet Bashikmajay He's another AA professor, and with Karen. But for now, we just have simulations using this dynamically extended unicycle model and a diffusion model that we estimate from this ETH data set for the human policy. I'll skip this one. Okay, so this is just an example here on the left plot. So we have a bunch of humans, the purple dots. They're moving according to this, diffusion model. In the left plot, there's no uncertainty adaptation, so you just assume they know the safety function outright a priori using standard CBF technique. You can see what happens is there's a collision. So basically, the robot agent is too goal-oriented and very aggressive, so ends up crashing. And then that causes it to sort of behave weirdly for a while as it adjusts before going to the goal. On the other hand, our online adaptation method is more conservative and eventually reaches the goal, but does it slower without collision. So this actually kind of exposes interesting questions about the trade-off between control and goal-oriented, reaching a goal versus how much you care about safety. So these plots, they're a little unfortunate the way they're chosen to be plotted, but the top right-hand corner is better in both plots. So this is like collisions, 0 better than 100, and then control effort, kind of a similar thing here. We're comparing standard CBF, same as the previous slide, a different baseline which uses a fixed safety margin, our method, and then MPPI, which is another common safety rule for multi-agent systems that just doesn't have as good of, or any, as far as I know, guarantees in terms of safety. What we can see in both of these plots, so one is control effort, one is goals reach, is that our method consistently is better in terms of collisions. So we have almost no collisions, and that amount sort of depends on the risk tolerance you set for lambda, in estimating lambda, the safety margin. But we have more control effort that's expended. We still outperform, and similarly for the goals reached, we still outperform the other two baselines. CBS, on the other hand, have they have almost 50% collisions, so like about 40% here. The difference in control effort isn't that much. Same thing over here for goals reach. They have a lot of collisions, but they almost always reach the goal compared to our method. So this is kind of interesting in the sense that maybe we should have, so we're already adapting to uncertainty online, but through one parameter that just focus on the data we gathered. Maybe there's more effective methods that can decide when to be more goal-oriented or control or minimizing control versus safety, depending on how reactive the agents are. So it's a similar kind of question to the end part of the first part, trying to understand and estimate how adaptive the agents are, and then use that estimate and your uncertainty about that estimate to more effectively design your control policy. So we're looking at that from a theoretical point of view, and then we're also deploying this, as I mentioned, in lab settings with robots, and then also in a high fidelity warehouse simulation for those mobile ground robots that move pods around on Amazon floors. Okay, so I'm almost done here. So just quickly, there's some interesting open questions on the conformal side that, I think I've talked to a few of you today. I'm very open to any collaborations. There's one in particular that I think is interesting. Well, there's two here that are interesting from a theory point of view. So first is getting a handle on the sizes of conformal sets as a function of your feedback mechanism. That is a very challenging problem. I understand that George and his students have a good kind of handle on that recently that I'm looking forward to reading. And then, of course, there's this idea of anytime algorithms. If you don't know, historically, actually, conformal methods were designed for what's called an E-value, which basically builds a super martingale based on the mean value of your stochastic process over time, and then sort of tracks what that accumulation looks like. So you're really kind of going after the mean, but you have a more dynamic view. You have some history built in. So this seems really more appropriate for dynamic systems. However, being mean focused is not good for safety. So on the other hand, these p-values are really a snapshot in time, so it's just instantaneous, but they're tail focused. So they are better for safety, but they don't have this dynamical systems perspective. And you can get anytime algorithms for e-values. So the question is, can we combine these two? Like, what's the right way to do best of both worlds? I'm not really sure personally yet, but I'm that's percolating in the back of my mind. So happy to discuss with you. All right, so I think I'm out of time anyway, but just wrapping up, we talked about these issues of non-stationarity, lack of uncertainty adaptation. This is increasingly important as we build AI agents into our control systems, our robotic systems. And so some of the things we're thinking about, specifically with respect to the work I talked about, is extending these cases to having like the principal agent problems, or even the first part of the talk where we have agents dynamic updating. So not just having dynamics for the agents learning themselves, but the environment changing too, more traditional control kind of things. And then, as I already touched on, more intelligent or strategic feedback aware uncertainty quantification. So I'll stop there. Definitely would like to cover some more open questions, but I think I'm out. So that's it.
So in the second part, you get the policies of the other agents. How good are those policies?
It depends on the data. So haven't implemented it in any real world context, but it is my understanding through working with Karen that this ETH data set for pedestrians is fairly comprehensive. And so, yes, I think it fundamentally depends on how good that initial estimate is. And I don't have any good theoretical results that kind of bound that.
And is it on a variety of environments and scenarios?
Actually, I'm not sure what is all in the ETH data set. My understanding is it's just pedestrians, which I think that means probably roadways in Europe, but yeah.
Right.
Yeah. Any other questions?
Maybe one question about the first one. I guess because the one result which we asking the second result, that leads to a need to determine the step size, which depends on the response of the agents.
Mm-hmm.
So how this, and how you estimate the cost of steps? Maybe then.
Once you have the guarantee that the agents that you've deployed the action long enough that the agents stabilize up to the noise floor. So in theory, we can prove that that's possible with our bound on what tau needs to be. Then it's just standard techniques and stochastic gradient methods. So you choose step size with respect to the noise in your system and whatever kind of local convexity you might have, or global convexity.
Thank you.
Any other questions? Thanks. Well, I appreciate the opportunity to talk.
And I just
Thank you.